In this video, we're going to look at ranking substances based on melting or boiling point. In this particular example, we're going to rank these 4 compounds by highest melting and boiling point. And so I need to think about the intermolecular forces. The compound with the highest intermolecular force, the strongest intermolecular force, will have the highest melting and boiling point. And that should belong to the ionic compounds. Ionics have the strongest interparticle attractions because you have oppositely charged ions that are highly attracted to each other. So the first question I would ask myself, are there any ionics? And I know a compound is ionic because it should be metal, non-metal. And so if I look at this list, I see a lot of nonmetals, nitrogen, carbon, hydrogen, but potassium chloride. Potassium is a metal, chlorine is a nonmetal. This should be my number 1 highest melting and boiling point. The potassium chloride is an ionic compound. So we'll have strong attractive forces from the oppositely charged ions. The rest of them are covalent. And of the covalents, we can rank them as polar or nonpolar. So my second question, are the covalents polar or non-polar molecules? Are they polar or non-polar? The rest of them are all non-metals, so I know they're going to be covalent compounds. But are they polar or non-polar molecules? And for that, blast from the past, we might get to draw Lewis structures. Yes! Okay, so let's draw NH3. So I have nitrogen, and it has 5 valence electrons. Do you see how there are some concepts that you just can't hide from? Like bonding and all this good stuff. It just never goes away. It affects so many properties of the particle. We'll add the hydrogen. That's easy. 3. All right, and then we'll draw CH4. Carbon has 4 valence electrons. So we'll hook on the 4 hydrogens. See, this isn't so bad. 2 and 3 and 4. And the last one is just HCl. Easy, right? 1 valence electron for hydrogen, 7 for chlorine. 7. Connect the dots. There we go. Okay, so we want to look at the structure and decide if these are polar or non-polar molecules. And so one of the things that we had mentioned was if you have a central atom, kind of like nitrogen and carbon, we're looking at the arrangement of the other atoms around the center. If they're evenly arranged around the center, even though these bonds might be polar, an even arrangement would cause those polar bonds to kind of cancel so that overall the molecule becomes nonpolar, such as the case with NH4. This carbon-hydrogen bond is a little polar because the atoms have different electronegativities, but they're arranged evenly around the center in that tetrahedral structure. Or you might remember, it's a 3-dimensional structure. It's kind of like that little rocket ship, tetrahedron. Since all 4 hydrogens have the same electronegativity and they'll be at equal angles around the carbon, the little poles cancel, and this becomes a non-polar molecule. Non-polar molecule. However, if you have something like nitrogen in the center, it does have 4 regions of electrons around that nitrogen, but one of the regions is not really an atom, it's a lone pair. That will give you, do you remember that trigonal pyramid shape? Where it's kind of like a tetrahedron. These angles are similar, but up on top you have a lone pair instead of another atom. So the other 3 atoms are not arranged evenly around the center, and this is a polar molecule. Now if you have something like HCl and there really is no central atom, if the bond is polar, the molecule is polar. So if I have 2 different nonmetals, they'll have different electronegativities, and this would be a polar molecule. All that comes back to me, blast from the past. So often it helps to draw the Lewis structure. If you draw the Lewis structure and you have lone pairs on the central atom, it is automatically a polar molecule. That lone pair represents a spot where you could have another atom and you don't. So your remaining atoms will not be evenly arranged around the center. If you only have 2 atoms, if they're different nonmetals, then it's polar. If they would be the same, if it were like hydrogen-hydrogen or chlorine-chlorine, then that's a nonpolar molecule because they would share the electrons the same. And we really wouldn't have a region that's partial positive or partial negative. All right, cool. So now we can kind of continue to rank these. The second strongest form of intermolecular force is the hydrogen bond. Hydrogen bonds occur between polar molecules, so we're looking at HCl or NH3. Polar molecules that always have a region that's partial positive and partial negative. The nitrogen is always partially negative. It has a high electronegativity, so the electrons are drawn toward the nitrogen, and there's a lone pair sitting up there, which then means that the little hydrogens are partially positive. This is a polar molecule, and the atoms will be very attracted to each other. Now, because it is nitrogen bonded to hydrogen, this is a pretty extreme dipole. Hydrogen bonding occurs between molecules that obviously contain hydrogen, but the hydrogen has to be bonded to FON, the 3 most electronegative elements on the entire periodic table. So this is a really extreme dipole. It's not quite as strong as a complete transfer of electrons like potassium to chlorine, but this is going to be a strong partial negative and a strong partial positive. That's your hydrogen bonding. So number 2, if I'm ranking these, will be the NH3. It's going to have hydrogen bonding. Remember, that's going to be hydrogen bonded to FON. Awesome. Then the next strongest intermolecular force would be your dipole force. Dipole forces are for all other polar molecules. So like my HCl, where my chlorine has a stronger electronegativity, so the electrons are drawn toward chlorine. That has 7 valence electrons, really wants 8. But yet the hydrogen also wants 1 more. Hydrogen has 1, he wants 2 to fill his outer energy level. That chlorine just has more electrons or more protons in the nucleus, so there's a stronger attraction for electrons. Partial negative, partial positive. It's a polar molecule. It's not as extreme as the hydrogen bond, which would be hydrogen bonded to FON, but yet these molecules would be highly attracted to each other. The opposite ends of the HCl molecules would attract. So my third highest melting and boiling point would be the HCl. This one has your dipole forces. And I guess the loser in this battle would be the nonpolar molecule. The nonpolar molecule does not have any substantial region of partial positive or partial negative. These individual bonds might be a little bit polar, but due to their equal arrangement around the center, the atoms, or I should say the electrons, really are, for the most part, evenly distributed around the central carbon. Now, electrons are always moving, and so if by random chance the electrons for a split second in time are not evenly distributed around the central carbon, then we could get a temporary dipole, a temporary partial positive or partial negative. But it doesn't last for very long because the electrons are moving. And the majority of the time, these electrons will be evenly distributed around the carbon. But if for that split second in time, there is a temporary dipole, that would create the London dispersion forces. Or if you want, you can call them LD forces. Those are the weakest intermolecular forces. So these particles should have the lowest melting and boiling points. The attractive forces between the particles are weak, so it really doesn't take a lot of energy to separate the particles and change phase. So if you need to rank particles for melting points, boiling points, you really need to think about their molecular structure. If they're ionic, they have the all-time highest attractive forces, and they'll have the highest melting and boiling points. If they're nonpolar molecules, they'll be the lowest. They have the weakest intermolecular forces. And then between the polar molecules, ask yourself, are there any molecules that have hydrogen bonded to FON? That's a special form of dipole force. We call them hydrogen bonds. They're polar molecules that have very extreme dipole forces, which makes the intermolecular forces a little bit stronger than your typical dipole force.